You have to remove the mute.
Now you're not muted.
Okay. Okay.
Hello to everyone. The first speaker today for this session is Professor Ricard Devesa. He's an analytical chemist and head of the analytical laboratory of Barcelona Water Supply Company for 20 years. Now he works as a freelancer for that company and others. He's also adjunct professor at the Chemical Engineering Department of the Polytechnic University of Catalonia, Spain. He is the leader of Working Group 1 of our cost action, dealing with advances in sensory analysis of water, taste, and odor compounds. And he is an expert in that field. The title of his presentation is Sulphates Give Water a Bad Taste. Really, Ricard, the floor is yours.
Thank you, Theodoros, for your presentation. Okay, one of the objectives of our action, of our cost action, is the translation of the taste and odor wheel. This wheel is the core or the flavor profile analysis method described in the standard methods of the American Water Works Association. It is a descriptive method, so it means that tasters have to describe, to indicate the main descriptors that they detect when they drink a water. This wheel is divided in 3 main sections. Please. Excuse me, there was certain noise, and it's for me difficult to speak if I'm hearing some noise. As I was telling you, we have 3 main sections. The taste section with 4 families: bitter, salty, sweet, sour, and acidic. Then we have several families of odor, chemical, hydrocarbon, miscellaneous, medicinal, phenolic, fishy, rancid. All these families have different origins, be natural or be anthropogenic. As it is well known, the natural odor causing compounds more frequent are geosmin, are methylisoborneol, with earthy, musty odor, or in the case of tap water, chlorinous is the most common. In addition to that, we have the feelings of the sensations, like chalky, pungent, metallic, refreshing, and we detect it at the oral cavity. So we refer to taste of this that we detect on the tank. We say odor when we detect in our nose, in the pituitaria, be by ortho or retronasal way, and the sensations. When we say flavor, we refer to the overall impression, the integrated sensation that we have when we drink water. Even though usually we use taste and flavor are synonymous, but technically is not correct. Taste is just what we detect in our tongue. Flavor is the integrated sensation, okay? The taste and odor wheel has been extremely useful for the water sector. It was the first version of the wheel was issued 30 years ago, more or less, and this wheel is updated continuously every 4 or 5 years. The last wheel is from 2017, and I suppose that in the next edition of the water analysis book of the American Water Works Association, this will be improved with new compounds. This will permit us to classify the different molecules that give taste and other. Obviously help to have a common language for water utilities, for researchers, for consumers. Obviously, it's a good way to disseminate the advances that the sector has in taste and other issues. It's a huge, it's very useful to solve taste and other events that obviously are very common in water utilities, be from anthropogenic spills or from natural sources. In this, I like to insist that a good collaboration between chemical analysis, organic chemical analysis, and sensory analysis is crucial for good to solve these events, which are a big problem for water utilities when they present, and also to include the matrix water in the portfolio of taste and odor wells. The water sector obviously is not a pioneer in the sensory analysis. In other foods such as wine, beer, chocolate, they have been working for several years, and we learn from them. In fact, the taste and odor wheel of the water was not invented by our sector, but was inspired on water by water from beer and wine. In sensory analysis, we have several kinds of test methods, and they can be classified with different criteria. One of this, I like it, but I understand that there are other classifications in the literature, is descriptive techniques, as the FPA method, the taste and odor wheel, which try to describe to give the sensory profile of a certain sample. Okay. Other methods try to detect the odor threshold concentration or the taste threshold concentration, which means that the minimal concentration that humans can detect. It is important to say that humans have a very different sensitivity against taste and odorants. So when we say threshold, it means the mean threshold, or the threshold that corresponds to 50% of the population. But it means that we can find differences of 10 or 100 times because in individuals. So the reproducibility of these thresholds is very low in comparison with chemical analysis, for example. Also, another difference is between detection and recognition. Detection is when we say, yes, this water has a certain odor, but I don't know how to describe it. I cannot say what odor is, even though I feel that it's a little different than the blank. Recognition means that I detect it, and in addition, I say that water remembers me nuts, or remembers me cucumber or acetic acid. And sometimes it requires an increase of concentration from detection to recognition. From my experience, I would say that the usual factor comes from 4 and 10. Maybe 4 is the most common factor, at least in our experience and in our water field. Other techniques are affective, hedonic, acceptance, preference, and the answer is: do you like this sample? Will you drink it? Or if you have some waters, which one do you prefer? These techniques are very, very important for the water sector. Obviously, is the main issue of a water company. Are you willing to drink this water, or you say no, that's awful, and I have to buy bottled water, which is very expensive and with a big impacts on environment. Okay, and the last one, difference test. The objective of this test is can you discriminate one sample from the other? This is also very important for the water utilities. The question is, I'm going to change the resource of water because these wells have no water, and we are going to take water from the river. The chemical composition of the waters are different. So the consumers will be sensitive to that, will discriminate. We will have claims about the consumers, or we are going to introduce membranes in our treatment because we need to improve the quality of our resource, but because the water doesn't comply with the European directive. Or we have a scarcity of water and we have to introduce desalinated water from the sea, for example, in our water supply system. What will be the reaction of the consumer? From my experience, the reactions is always bad. because people is used to a certain degree of mineralization, and when you change the quantity of minerals, you have problems, and you can explain to them that the water has a better chemical and microbiological quality, but the customer says, okay, you are right, but I don't like. So different tests is very useful in these situations. And one common policy is to blend the waters in such proportion that customers don't claim, don't find the difference. Okay. Today we are talking about taste, not about other. In general, most of the literature refers to others because we have a lot of compounds that gives other to water, organic compounds. But sometimes also it's interesting to pay attention to inorganic compounds, which are detected on the tongue. So it's a taste issue. You can see here the main minerals in water: sodium, potassium, calcium, magnesium, chloride, sulfate, bicarbonate, and the TDS, the total dissolved solids. It means the total quantity of dissolved minerals that we have in water. Some of them give different descriptors: salty, bitter, astringent, gypsum, chalk, etc. One important thing, here you can see the threshold taste concentration, and these quantities are in milligrams per liter of the cation or the anion. You can see that we are talking about milligrams per liter, but if we were talking about others, the concentrations are very, very low, are in the range of micrograms, even nanograms per liter. So it means that when we talk about taste, our concentrations are 100 or 1,000 times bigger, okay? For that reason, some of these parameters are regulated in the different legislations. Here you can see the legislations from the American, from the European directive, and from the guidelines of the World Health Organization. I have to say that this slide has not been updated. We have now a new European directive, which was issued on January, but there has been some changes. But in these parameters, there has not been any change. They have maintained the same values. The taste of a water, it's very a complex issue because we have several cations, several anions. The threshold depends on several things, but in addition to that, there are synergistic and antagonistic effects between cations and anions. So every water has its own character, its own taste. There are not two waters with exactly the same taste. Even though the sensitivity of humans about taste is not very good. in comparison with the others. Some people says I like this bottled water, and when I change, even though the resource is the same, I detect it. Most of the times, it's a psychological problem. You see your bottle, you see your brand, and you say I like it, and I don't like the other one. But in some trials, in blind tests, without showing the brand, the result is that people sometimes cannot discriminate between waters, even with different chemical composition. So with taste, people used to be not as sensitive than with others. We have positive or negative effects, synergies and antagonists between species, and the results in the literature show big discrepancies, and there are several reasons for that. The temperature of the test, obviously, with cold waters is more difficult to detect differences. The type of testers, we are talking about consumers, untrained people, or trained or professional panels. The results are quite different. The age, what is clear is, even though, at least from my experience, we have not found difference between men and women. Obviously, we have found big differences between young and elderly people. When you reach at 60, your sensitivity goes down. So for better results, you have to need a population which is representative or about the purpose of your study. The sensory method, that's the most important thing. Historically, several sensory methods have been used with different statistical treatments. So these methods reach to different results, sometimes in a significant way. And also, for example, the reference water. Always a water testing is done in relationship with a reference water or a blank water. Do you like this water? Yes or no, in comparison to this one. Depending on the reference water, the results can be different. Okay. That's one work that I published with Andrea Adretic some years ago, and the main conclusion is that in general, when the TDS increases, people dislike it. So when you drink a water with more TDS, with more dissolved salts, then the tendency is that the liking of the water goes down. And we deduce a factor of 0.23 units for 100 milligrams liter. Some comments. Here you can see all the results. concerning to several studies performed in Barcelona and in Virginia. You can see that sometimes the adjustment is very good. Sometimes you have a high dispersion because obviously the taste of the water depends of a lot of things. The organic content, the chlorine content, the presence of some metals. So that's just a general trend. On the other hand, this study is from I don't know exactly. Well, I mean that waters with very low TDS have not been included because in Virginia and in Barcelona we don't have these waters. But I'm sure that if waters with very low TDS were included, then there would be a decrease of the lichen at the beginning of the graph. That is, waters with very low TDS, some people like it, but some people don't like it. So I think the graph, we will have a maximum about 100 milligrams per liter or 50. So we have to clarify that, but because this tendency probably will be broken at the beginning of the x axis. Okay, but the question is, here we can see the behavior of the TDS, but the TDS is an integration and an aggregation of all the dissolved minerals. But which is the role of individual minerals? So we have some minerals that are negative. Sodium, chlorine are negative. Pardon? Yes, but other ones are positive or unfavorable. The precedent of this speech was a paper where we detected that there were some positive elements like calcium, magnesium bicarbonate, but sulfate, nitrate, and silica were also positive. And we want to work on that because sometimes you have spurious correlations. So let me explain a little. We detected the threshold. There are several methods. We use in this study the three alternative choice, and you can see that the yellow cells show the first concentration at which every panelist consistently detects the stimulus. And you can see that even they were trained panelists, there are big differences between individuals. But it gives us a geometric mean of 110 milligrams per liter, in this case of nitrate. Another method is to represent the percentage of detection, and you see that the 50% perception is 109, so there is a good correlation between both methods. So nitrate is not relevant for taste and odor because you see that the thresholds are above the sanitary level, which is 50. So nitrate is a problem for health, but it's not a problem for taste and odor. With sulfate, I'm going to skip it. With sulfate, things are different because you see that the geometric mean is 159 or 83, depending on the water that you have taken as a reference. As I said before, this aspect is very important. So it means that sulfate can have some effect about the taste of water. Sulfate has been traditionally considered negative, very negative for the taste and odor, but in this slide, we see the results of a duo-trio test where panelists are asked if they prefer a water speak with sulfate in comparison with water with sulfate. In green, you can see the samples. Sorry, in green, you can see the situation where a panelist says that prefers the water speak with sulfate. In yellow, when there is no preference. And in red, when people says water with sulfate, I don't like it. Cells in white means that the panelists didn't choose the different sample. So in this case, these cells are not taken into account. So you can see that on the right side, you have when the situation is that people don't like sulfate, but on the left side, you can see the green cells, meaning that people prefers water with a small quantity of sulfates. And you can see here that the reversion situation is about 250 milligrams per liter. So it means that even though sulfate is considered bad, and obviously when waters have a lot of sulfates, they are chalky, even they are bad for health because they are laxative. In moderate concentration, it seems that the sulfate it's even good, it's neutral or even good for the taste. Okay, and that's it's in accordance with a previous paper by Dietrich and Burlingame. In this paper, they revised the organoleptic parameters covered by the American legislation, and they conclude that probably it would be necessary to change the red cells, so it means chloride, copper, and iron, but sulfate, 250 milligrams per liter, it is okay, because at this level, the role of sulfate is not negative. It is neutral or even positive. So I'm happy for my contribution to show that sulfate is not necessarily bad for water. Obviously, in low or moderate concentrations. Okay, thanks for your attention, and I will try to answer to your interesting questions.